topic of the talk is the Fedimint Consensus. I want to achieve two things here. So I want to give an intuition for the design that is at the heart of the Fedimint Consensus, or at the heart of the Fedimint system, and I want to lay out how this then translates over into the performance characteristics you see in these distributed systems, especially with respect to latency and reliability and the fusion of those reliable low latency. Yeah, so as I said, there's time for questions planned into this. So if anything is unclear at any point, maybe just raise your hand and then we will address it right away. At the heart of the system, we have the fundamental problem similar to Bitcoin, that we have a bunch of transactions coming in and we need to establish consensus on the order. And that problem has been worked on for like 30, 40 years in distributed systems already. And they call it the atomic broadcast problem. And there are like various algorithms already which solve this problem with different characteristics. And so this was already working when I joined the Fedimint project 18 months ago. But we are using a different algorithm than we are using now. The fundamental thing that this algorithm is solving is establishing consensus on the total ordering, and it is supposed to do so in a Byzantine Fault Tolerant fashion. That means up to 1/3 of our peers, or of the nodes, can be malicious, and the system will still work. In practice, they won't probably not be malicious, they will just be offline. Furthermore, we want to do so asynchronously. So we don't assume any limit on the latency between the peers. Yeah, we cannot assume that like within 5 seconds we get a response or something like that. This is not really realistic on like residential internet connections. And in our case, we want to have the low ordering latency. What the ordering latency is the latency between a transaction being submitted by one of the guardians to the broadcast and it actually being ordered. This is important because from the client's perspective, a transaction is only final after it has been ordered. Yeah, so low ordering latency is very important for us. When I joined in like April last year, we were still using the Honey Badger BFT. Some of you maybe have heard of it, which is an algorithm that solves the atomic broadcast problem. It's built on a mechanism called asynchronous common subset, which roughly works that you have rounds of a few seconds. In every round, every one of the guardians proposes a batch of transactions to submit to that round, and then the guardians start voting which ones are going to be included in that round and which one are going to be excluded in that round. And when this voting process is complete, you take the union of all the batches of transactions that were submitted, and this is your common subset, and then you can start processing this. This system has had a logarithmic latency, so logarithmic in the number of peers, and it had one more issue. You see here in the equation that f is the faulty number of peers. So as soon as f is non-zero, you have this immediately latency jump. Intuitively, this comes from the fact that if one of the guardians is not submitting any batch because it is offline, then then every time you need to separately vote on this batch not being included, and then this just takes longer. Furthermore, this algorithm required a reliable networking layer, which means that all messages between guardians are delivered in order. So you need to retry and then acknowledge messages between peers. This is often the case in the literature, since they just at the start of the paper assume unbounded message buffers, which is in practice very much an issue because no buffers are unbounded. So yeah, this argument was not that practical. The reason the latency was so high because in its design it was explicitly disregarded. It was thought of as a replacement for Bitcoin itself. So they were focused primarily on throughput, not on latency. It was not thought of as a foundation for a fast payment system. The solution to this was switching over to another atomic broadcast algorithm called LFBFT. Yeah, this works internally very different. It is part of a class of algorithms that use directed acyclic graphs to represent the communication history of the guardians. We'll get to that one in the next slide, how exactly that works. As a result of that, the latency of the algorithm is constant, the ordering latency, with respect to the number of guardians. So your latency does not go up significantly even if you have like 10, 15, 20 guardians instead of just 4, which is the minimum. Furthermore, you don't have this latency jump anymore if one of the guardians goes offline. Yeah. The expected ordering latency of this algorithm is 5.5 times the one-way network latency. So if you have an average latency between guardians of 100 milliseconds, then the time for a Fedimint transaction to be ordered and therefore finalized is 550 milliseconds. We don't need the reliable networking layer anymore. Yeah. Yes. Yeah, all guardians maintain a direct connection at all times. Bradley?
If that's the expected latency, what's the worst case?
What do you mean? Oh, yeah, so there's a tail, obviously. You could derive a latency distribution, like formally you could derive a latency distribution from the latency distribution of the individual peers. However, you would find that the good thing here is even if you have like long tails on the individual latency distributions, the tail of the total ordering latency will be much shorter. Yeah. So the downside of this algorithm is, no, we don't need the reliable networking layer anymore. So messages that can be delivered out of order, they can be dropped. The LFBFT internally implements all retries necessary, so that this makes us much more practical. Downsides is we require a session switch every few minutes. So because while the algorithm runs, it consumes RAM proportionally to the time it has been running, and every few minutes this might get out of hand. And therefore, we need to do like a synchronized session switching where we have like a short latency spike. That's why this class of algorithms is not as common, at least that's my impression, even though it has many benefits. In the literature, this is rarely used because of that theoretical downside. However, in practice, it is nearly negligible in our system. It's not really a problem. Yeah. Okay, so that's what the communication graph that is built internally looks like. So while the system is running, every guardian, so at the beginning, every guardian creates those genesis nodes in the graph. The nodes in the graph are called units. That is, we got so many nodes here, I'm going to stick to the name units for those. So we got those genesis units here. They are generated, one per guardian. And then the guardians start to exchange those units. And every guardian waits until it has a threshold of units from the previous round. So this is around round 0, round 1, round 2. Time goes from left to the right. It waits for a threshold of units from the previous round, and then it links those as like parents of the unit of the current round, and then moves on. It waits at least 50 milliseconds to do so. So if you have a one-way latency which is lower than 50 milliseconds, you will have a round time of 50 milliseconds, 20 rounds a second. If the one-way latency goes over 50 milliseconds, those round times will become bigger accordingly. The graph structure that you would see here, just from the graph structure, you can tell that the first guardian, the one in the upper row, is the slowest of them, because the lower three guardians, lower three units, they all only reference the lower three units, because those three guardians are faster connected. You would see such a pattern, for example, if the lower three guardians are in Europe and the upper guardian is in North America. So in that case, the lower three guardians, they would drive the system. And that's where very fundamental latency characteristic comes in. The system will, okay, so the system will always progress at the speed of its fastest threshold of guardians. So if you have like a 3 out of 4 federation, the fastest 3 guardians will drive the system. If you have 5 out of 7, the fastest 5 guardians will drive the system, and 7 out of 10, the fastest 7 guardians will drive the system. Those fastest threshold is not constant, so you could have like right now you got like within 1 second or less, the fast like guardians could come and go into this faster threshold. So if if one of them here, let's say the lowest one, would experience a latency spike that would drive up its latency, let's say like 500 milliseconds, so it becomes then suddenly larger than the latency of the first guardian marked in red, it will automatically switch, and the upper 3 guardian will start driving this, like progressing the system, while the lower one is only delegated to like an observer. Yeah. That is very practical in deployments. What we don't want, what we had with the previous algorithm, is that your system's latency is kind of dependent on the slowest guardian up to a point. Here, this is not the case anymore. The latency of your system actually becomes more reliable the more guardians you have, because you can tolerate like more and more guardians that have like high latencies, but you don't need them right now. And imagine, for example, a system deployed on residential internet connections. Guardian might be correct and it might be online, but you have a suddenly latency spike when your network gets clogged or something. We just have like 300, 400 milliseconds of latency, and you don't want your users to experience that. Yeah, so you can see how the latency characteristics of the entire system are fundamentally derived from this graph structure. So yeah. Yeah.
Can you explain the graph again? Does it show multiple points of time, or does it only show 1 point of time?
This is the graph of how the third guardian would have this graph locally in its RAM, and so like observed at like 1 point at a time, and it would like units would be continuously added to the right side of that graph, and that graph would grow to right 20 units at a time. 20 rounds a second, and therefore, in that case, 80 units a second. Since we have
Sort of message history.
yes, yeah, it is exactly the message history between the guardians. Yeah.
Yeah, I think interesting to mention is that like guardians are sending these units no matter if they have something to contribute to consensus or not. Like only
Yeah.
some of these units will contain actual user data, but like all of them refer to like I think they all commit to the previous units that have been seen by that guardian.
Exactly.
I think like in this graph, for example, eventually
No, actually not. No, no. That is not necessary. No, like if the first guardian is the entire, like, is always the slowest one, it would never be its units would never become ancestors of the first guardian's units. Yeah, you might be wondering yourself. You might be wondering, why are we talking about units? Where are my transactions? So the transactions will be attached as data in, or can be attached as data in those units. So it's like 50, you can attach up to 50 kilobytes of data per unit. Yeah, so one megabyte of data per second per peer. And
Spend a lot of time without. You can continue. I can ask like what you have later.
okay,
A lot of questions about
yeah, we can do like one or two more questions. There's like,
colors mean.
sorry.
The colors. What do the colors mean?
The colors just, the red ones mean this one are the units by the slow guardian. Yeah. So the upper, like every row is one guardian, and the red row is the slow guardian in that case.
What do the arrows mean?
The arrows, yeah. So the arrows are like, they are the ancestors. So by hash, this unit here marks those three units as its parents, as its ancestors. So they commit to them by hash.
And what does that mean? Like I know technically what it means, but like, why would you mark something as your ancestor?
You mark them as ancestor because it says I have them locally available. I have downloaded those units, and I have the units and their attached data locally available, so I can commit to them. Yes, yeah. So they need to be like, the data needs to be locally available, because if enough later units point to this unit here, if a unit is several rounds deep in the graph, so if like enough units have been built on the right on this unit, then it will be ordered, and then the attached data will be returned by the algorithm. So we need to make sure that if a correct node returns this unit here as ordered, it needs to be available not just in one guardian, but in sufficient number of guardians so you can guarantee its availability to the other guardians. Yeah, that's why. So the marking a unit as a parent says I have this unit available, I have put it on my disk, and if it gets ordered, I can always disseminate it to other peers, and then they can order it, and it can be processed. So it's like a data availability thing. Yeah. Okay.
The session is started by one of them round robin, or?
So we do those session switches every 2 minutes, or sorry, every 3 minutes or more, and so like in the beginning, all guardians are equal. They just produce. It's not like there's a leader chosen in the beginning, and they just start creating those genesis units, and then they start broadcasting them, and then they start like building on top of them. Yeah. On the right side. So that is just because that would be so obviously we can't have consensus on the exact graph among the guardians. So every guardian has its local view of that graph, and this would be the view of the third guardian that has just created its new unit. However, it has not received the units of the same round from the other peers yet. Okay, so the properties that this gives us are the following. Any guardian can be killed at any time. There's no shutdown procedure whatsoever. You just kill the process. You can also just restart the guardian anytime and will automatically rejoin consensus. And if it is fast enough, it will, if it is part of a faster threshold, it will again drive the system forward. as I said, every few minutes we have to switch sessions. And when we switch sessions, we will take all the transactions that were valid and have been accepted in that session. We will compute the Merkle root of them, and then we threshold sign that Merkle root and persist it to disk, where it will be forever become the history of the federation. So very similar to Bitcoin, though it's not a blockchain though. We have this we have this history of transaction in a form of like blocks on disk. This history of we call them signed session outcomes can be used by any of the guardians that has had his database corrupted to recover just from a static configuration file that was created at the beginning and can be saved to an USB stick separately. And it can download the history of signed session outcomes from its peers, completely rebuild its database state, and automatically rejoins the consensus. And again, if it's part of the fastest threshold, we'll start driving the system forward. Yeah, okay, next point is ordering latency, already mentioned that. The entire, like, as I said, the algorithm itself is asynchronous, and we maintain this property in the rest of the system. So there are no like timing assumptions built in there. And due to its asynchronous nature, the system will perform optimally in any network latency scenario. So it's not like we assume, okay, we get a response within 5 seconds, and if we don't get a response within 5 seconds, we trigger like some backup pass or something like that. Or like performance drastically then slows. No, we will always have the 5.5 times of the one-way latency expected ordering latency. So the structure of the graph will always naturally adapt to the network latency scenario that we see, and make efficient use of that in order to progress the system forward. Yeah. Okay. Okay. Any questions to that one? Yeah. Okay. Yeah. Yeah. If we have just one guardian left, how do the other ones recover?
The others, they lost the database.
And then the last guardian also loses database?
No, the last one is fine.
Well, one guardian by itself cannot progress the system, it would stop. And then it would wait for the other peers to recover from it would start broadcasting the signed session outcome to the peers, and the peers would rebuild the state, and when they catch up with him, then the system would start to progress again. Yeah. Yeah, there are some intricacies, so if like so many people lose their database, but if so many guardians lose their database, but yeah, that's how it will work. Chris?
So the communication graph from before is different for every guardian, depending on which messages they receive?
It will eventually converge because they broadcast it to the other guardians, but at any point in time, they might have different local subgraphs of the total global graph. But the assumption is if I have a unit locally that I have accepted, I can broadcast it to my fellow guardians, and since it is a valid unit, they will also accept it and add it to their graph eventually. That might take time, there might be network issues, etc., but I can always, at some point, broadcast that unit to...
Something is lost, like with TPC, it's like sent again, TCP or whatever.
Yes, yeah. So the LFPFT internally implements retries, and it will start like every guardian. They continuously broadcast their highest unit for every round, and if a guardian sees a unit where it doesn't know the answers to, it will start request the unit from its peers. A bit of like you've seen a block and you don't know the answers to the block, you will try to.
How do we get the ordering from the graph?
Well, that's an excellent question. So we have a quite, it's a bit like a fork choice rule, but much more complicated since you don't have just a chain. But from, there is a rule where if a unit has been, so we want to choose a head for every round. So for this round, we might select this one, and then this one, and then this one, and then this one. Never this one, because they are too slow. They don't have enough children. But if a unit is about 5 to 6 rounds deep, then it usually has enough. Usually has enough children that list this as its ancestor, and thereby voting on it to become a head. And yeah, then it will be chosen, and then it will be ordered. So we might choose that head, that unit for head for this round, and then the transactions and this head, they will appear in the output as ordered. And then we chose this one as a head, and its transactions will appear as ordered in the output. And the tricky part is that for any local subgraphs of the total graph, is a correct peer chooses, let's say, the first one here as a head for this unit, when another correct peer chooses a head for this round, whenever that is, might be arbitrarily later, but whenever that is, it will be this head. So even if you have two local subgraphs, different local subgraphs, you know, which have a huge overlap, but they might differ in the last rounds. If two correct peers choose a head for that round, they will be agreement on, or they will have consensus, however you confirm. Yes.
For the nodes that have sufficient number of children,
Yes.
it's like a numbering.
Exactly, exactly. And this is a separate process. You have the networking layer that drives, in Rust, actually completely different tasks, so, or threads, if you want to say. So you have the network layer that just drives the creation of this graph. It's very stupid. It's just wait for units to come in, verify them, add them to the local subgraph, and if you have enough units for a round and 50 milliseconds has passed, then create a unit yourself and just put in all the transactions that you yourself receive locally. Yeah, so that is very simple. And then you have a separate task which just take the local subgraph as input, and it's a pure function, and you ask it, can you give me a head for this round? And then it says either, no, the subgraph is not big enough, I cannot choose a head yet, or it says, yeah, this one is a head here. And then you ask it, can you give me a head for this round? And for this round, and here, since you need about 5 layers, maybe if you would feed that in, this one would be chosen as a head, but for this round already, they would say the graph is not big enough. Yeah, and that's where this like latency comes from. This like 5.5 times one-way latency is, because you need like a unit needs to be at least 5 rounds deep in the graph to be chosen as a head, and then with every second round, the probability that it's chosen for that round is like 50%. So with 50% likelihood, it's already in the 5th round, and then with 25% likelihood, it's in the 2nd round, and then with 12.5 likelihood, it's in the 7th round, and yeah, so it might take 9 rounds for a unit to be chosen as a head, but this is exceedingly unlikely. Yeah. Any more questions on that? Okay, so far we've been talking about latency. That was our main focus. But in the description of my talk, I said, you know, we want to talk about constant performance in general with respect to the number of nodes. And here we want to dive in how this is achieved in one of our modules, namely the ecash module. Yeah, and this works very well. So in the system we have built, we have completely constant compute consumption and disk space consumption, no matter if you run a single Guardian system or if you run 4 or 5 or 20. Yeah, no matter the number of Guardians, an ecash signature will always be 48 bytes, and it will always be verified in the same amount of time. That is possible due to us building our cryptography on pairing cryptography, specifically BLS signatures. That is, for like timelines of cryptography, relatively new, so developed over the last 20 years, and it's just it is very practical. Technically, we don't have one curve group anymore. We have three. We have three curve groups of prime order, and we have a non-degenerate bilinear map between two of those curve groups to the third, and we use that to build signatures that have very nice properties that don't require randomness anymore. So we have deterministic signatures. Yeah. So, and I think Eric mentioned this in its introduction before. So if we want to issue an ecash node, every one of the guardians will create a signature share, and then the client will go to every single one of those guardians, ask it for the signature share, verify the signature share. We'll take a threshold of those signature shares, so like 3 out of 4, 4 out of 5 shares, and then aggregate it locally. And so we push out this aggregation to the client, because the aggregation is actually the compute it requires, and the number of signature shares it requires is linear in the number of guardians, and we don't want this on the server side. For a client, it's negligible in performance. However, if you would have like hundreds of transactions a second on the server, then this would become an issue. So that's why, like we had initially when I started, we had server-side aggregation, and you just have like by a multiple more compute and disk space consumption than necessary. And yeah, then I changed it such that the aggregation is in the client. And then the client aggregates its blind signature shares into one signature, which is 48 bytes and can be verified in the same time as a single SIG signature. Therefore, disk space and compute consumption of the ecash module is constant with respect to the number of guardians, and this will be the same for Lightning V2, which uses a very similar cryptography, just a bit more complex, to actually encrypt and decrypt the pre-image of HTLCs, such that for an incoming HTLC, a threshold of the guardians can decrypt its pre-image. And we use this, like in that case, the decryption shares for the pre-image will actually be collected by the gateway, which then puts it together to obtain a verifiable decryption of its pre-image. Yeah. Okay, and now it's just time for further questions. Yeah. Yeah.
From the last slide. So when a new client comes up, they just
Please.
when a new client comes up and they've been offline for a couple of weeks or whatever,
Yeah.
they then just get the aggregates of the shares for the last epoch or whatever, and then they are they're synced, or do they have to replay history basically?
Well, a client is only concerned with its own transactions, so if it has been offline, it doesn't care what happened in the time. Or do you mean in recovery?
I don't really know.
Okay, so if, yeah, then I form it as a statement, like clients are ever only concerned with the transaction that they created themselves, and they can specifically reference them by an ID. So they don't incur any cost by the use of the system due to other users. It's very much not like Bitcoin Core. Yeah, so if you don't make any transaction as a client, you don't have to like download any signature shares whatsoever. Yeah, only in recovery, then actually you have to go. As I said, we have the session history of like signed session outcomes, which the guardians use for recovery. the client also uses for recovery. So if you completely lost your data, all your backups, which makes this more efficient, you can just take your private key, 12 words, and you can download the entire history of signed session outcomes, which is probably on the order of a few gigabytes, and a really used federation, maybe like 10, 20 gigabytes. And you can obtain all the ecash that you have generated yourself, and then recover it, and then rebuild your balance that way. Yeah.
I have one question. So how are the rounds determined?
You mean in the graph again?
And does everybody,
Those rounds?
yeah. So like there are rounds where people send messages, but how do people, the people don't agree on when the rounds start and end, right? So everybody has a different clock, so how does it work?
As I said, completely asynchronous, no timing assumptions. You see a lot of atomic broadcasts that would say like a round is maximum like 20 seconds or something, and then we cut off and it is failed and we retry again, something like that. Rounds like are really only the sum of like the nth units. So like round 0, round 1, round 2, it is just determined, if a unit is part of round n, it's just determined by its like height in the graph. And if a peer moves to the next round, it will locally see, so let's take like this peer here. It moves to that round as soon as it has received a threshold of units, including its own, so 1, 2, 3, 3 out of 4. And if the last unit it created is at least 50 milliseconds old. But that is like a local measure. The 50 milliseconds are checked locally, yeah.
Okay, so I had a misconception, like I thought there are rounds and messages of this round are sent within this round, and then we go to the next one, but here the rounds are just the depth in the tree.
Yeah.
And even if I'm currently in round 5, I can still receive a message from round 1.
Yes.
That just took a very long time, maybe from the red guy.
Yeah, exactly.
And so this is what you meant by the graphs converging, because eventually I will get like everything.
Exactly.
Okay.
And actually the only messages ever sent are the units themselves. There's no like negotiation. It's not like I finished this round and I'm waiting for a unit. Like a peer will only ever broadcast its own unit and the unit it has received from other peers. So that makes the messaging layer, as I said, very, very simple. Just receive units, wait for a threshold, wait at least 50 milliseconds since you created the last unit, commit to the units from the previous round via a hash, and then add this new unit to your local graph, and then start broadcasting it, and move on. Yeah. So it's really just like a few hundred lines doing this. Yeah. Like, and then obviously like you sign your own unit, and so then the peers can like send this like signed units, disseminate them among each other. Yeah. So like, for example, if like this peer. The last peer goes offline at some point, and then those peers here, they can take the units of the last peer and then send it to the first peer, which was a bit slower. So it can still achieve the same local subgraph that they have. Yeah. So that's why the that's why the networking layer is unreliable, because the only thing that you need to do is like exchange units. Very simple, like kind of like your relay blocks. Yeah, also conceptually at least relatively simple. Yeah, I got a new block, here it is, I received it from someone else, I verified it, here you go, and then it's like, oh, this is the highest block I have, can give me its ancestors, here you go. It's like just very simple request response, and always like, so this peer, as I said, would be the local subgraph of the third peer, the third guardian. And it would always broadcast this unit, this unit, this unit, and this unit. Or right now it would broadcast them. You know, the highest units for every guardian. and then yeah, if the other guardians are missing units in between, then they would request them afterwards. Yeah.
Thanks.